translate French sentence.
This is not an accretion disk. You know René Magritte, the painter, the Belgian painter. Magritte. You know what I mean. It's not an accretion disk. It's a drawing of an accretion disk. You know?
Yes, I forgot we have the alarm. We entered the alarm just 2 minutes. When we entered the building, alarm. The alarm was on. Is police coming? What's going to happen now? They just called. And
the police.
They will give us 2 hours. So we have plenty of time.
That's enough.
Okay. This is an exceptional lecture. I was hoping to have the lecture outside, but we have no projector, and especially we are broadcasting this. Therefore, it's better to stay here, and at the end, the discussion we have in the garden.
Good idea.
Let's compromise. Okay?
Okay.
Needless to say, we are extremely grateful to the one. We had this great meeting in Lausanne. It was fantastic, and it's very unique. The person who we are interacting only since recent time, but I am absolutely astonished about the depth of his knowledge, the technical knowledge, and his enthusiasm for research. Therefore, it's a great privilege to have him for us. Take advantage as much as possible of him.
Thank you so much, Remo. Okay, so maybe my name is Roland Walter, and I am professor at the University of Geneva in the Department of Astronomy. So Michel Mayor is a colleague, but I am not working on exoplanet. So I will not say much, but a little bit close to the... You hear me? Yeah. Okay. So you see this wonderful picture of the sun, where we can see a lot of details, magnetic loops. We see where the particles are accelerated, etc., etc. And I have studied accretion disk.
Should I turn it off? Like that is very nice.
Yeah, there are more. You have more contrast. So I have been working on accretion disk since my PhD thesis, quite some years ago. And this is 3C273, so that's the only thing we see from accretion disk, and all the rest are drawing. We have never seen an accretion disk, right? So this is not an accretion disk. So I thought to myself I would like to see one before retiring. So we'll see if it happened or not. So
what is the other picture of that? The one on the right?
Is the sun. Detail of the sun. You see people doing solar physics, they have wonderful data. We have only point sources, which is a bit painful.
Constantino Sigismondi, who took quite a lot of activity recently on the sun, will be with us on Friday morning. And he will show us some of the pictures he did recently. Beautiful.
Yes. So we understand optics from Augustin Fresnel. So he made most of his work at the beginning of 19th century. And he realized that when you look at a point source through some optics, you see these rings around the source image. And you see the source image is relatively large. It's not a point source. And he understood that this was due to optical diffraction. And he also understood to have a measure of the of the possibility to separate two sources like this, and for that this is the resolution of your instrument, this theta, which is given in fact by the ratio of the lambda, the wavelengths divided by the diameter of your optics, diameter of your telescope. So for naked eye, you can do the calculation and you find that the angle is 40 arcsecond, so about 1 arc minute. And this explains why, although the humanity look at the sky since 6 or 7 million years, nobody has progressed very much, because they could see the stars, the sun, but you know, they were basically blind to that, because they didn't have the resolution. And when Galileo came, his telescope had a resolution of 0.1 arcsecond from the optical point of view, to which you have to add, of course, the atmospheric blurring, the seeing. But basically, that's the best you can do. And when you look at the current telescope, we are always within 1 arcsecond. And Galileo was already able to get that arcsecond. And then, of course, he could see Jupiter, the moon of Jupiter, and everything else. So we started to progress. Now the VLT, you have the 4 VLT here. They have a resolution of 0.01 arcsecond. But of course, you have to add the effect of the atmosphere, which is the main annoyance we have on the ground, because even in Chile, the average is around 0.7 arcsecond. So we cannot resolve anything that. It doesn't work? Okay. So, so I was mentioning the VLT, and the way to improve the resolution was to do the VLT the VLT interferometer, which work only in the infrared. That's because to do that, we need to do adaptive optics. That means we need to correct the wavefront for the deviation created by the atmosphere, and then you can go from 0.7 arcsecond to about 0.3 arcsecond, which is basically the maximum resolution that you can get, even though the optic, from an optical point of view, the VLTI can do a bit better. So we are at the level of milliarcsecond, which is basically microdegree. Remember this number, microdegree. That's what we are able to do with our telescopes. That's because we can do adaptive optics with infrared. You know, you can have mirror that deform and that can correct the wavefront to correct the effect of the atmosphere. They measure the image of a very bright star close by to the source you are interested in, and they can modify with small mirrors the shape of the waveform to make it flat again before arriving. But we cannot do that with optical, because optical wavelengths are too short, so this mirror cannot do this type of correction, and particularly so fast. So that's what we can do in astronomy. So you know all of that. So radio, interferometry, the Event Horizon Telescope, which is there, and the VLTI in the infrared, where you see an annulus of dust around an active galactic nuclei. The most impressive image are, of course, the one of the Event Horizon Telescope. Here you have M87. So this was done with radio telescope located all over the planet, so a baseline of 10,000 kilometers. And with that, in particular in polarized light, you see this line are the line of polarization around in the magnetosphere of M87. So this is synchrotron light. And in synchrotron light, the magnetosphere, the polarization line are perpendicular. Draw the magnetic field line like that, as I did in blue, perpendicular to the polarization light. And you find, in fact, of the black hole, which rotate because of the frame dragging, because of the rotating black hole. And then assuming that you have a black hole, assuming that the radius of this hole is a square root of 27 Rg, then you can determine the mass, the accretion rate, etc., etc. And you find it in particular that the accretion rate is extremely low, 10 minus 6 Eddington ratio, while the power of the jet is 10 to the 3 m dot c square, which means that, of course, the is not coming from accretion, but is coming from the rotation of the black hole. Now, what I would like to do is to observe the accretion disk in cataclysmic variable. That's the easiest in active galactic nuclei, maybe in low mass X-ray binaries. And so all of that in the optical. And currently, you remember that we are at micro arc second, so that's the limit we have in the optical now. So that means we have to increase our resolution by a factor 1,000 to 1,000,000 to be able to do that. It's an enormous change. And of course, if you can observe accretion disk, you can also detect, make images of supernova that are exploding within 100 megaparsec, and we have one per month that is doing that. You can also resolve the optical jet at very close to the black hole, for instance, and one can do other things. So this is a list of targets that we could try to study. I indicated the angular size of this thing. You see it goes from nano degree to maybe femto degree. And this is this is the telescope diameter, or the distance that you need between the different telescope, that goes from, let's say, a few kilometers to 20 kilometers to maybe 5 million kilometers. So let's see what we can do. I am not going to go through all the lines. But obviously, we can look at massive stars. Massive stars are relatively large. They are micro degree to nano degree, so one can resolve stars. We can look at the feature on the surface of stars. Earth-like exoplanet on Alpha Centauri AB, so that would be the closest Earth-like exoplanet. This is 15 nano degree, so this would require a telescope, or a distance between telescope for interferometry, of only 1.5 kilometers. And if you go then accretion disk around white dwarf, or the white dwarf themselves, with a few kilometer baseline between telescope, you can start to resolve them in interferometry. Remember that between the VLT, currently the VLTI, we have only 80 meters from between the 8 meter telescope. And that's why we cannot go to this type of resolution. Then if we could go to, that's typically the distance between the VLT, the 4 VLT, and the ELT, the 39 meter telescope, which is being built in Chile. Then you can start to look at supernova, supermassive star. You know, we have, it seems we have stars that are several hundred solar masses in the galaxy, not too far away, and the question is what they are. So if we cannot resolve them, we don't know. Accretion disk of quasar, if we have with this baseline, you can resolve the accretion disk of 3C27. Disk jet connection, imagine that we see changes of the jet, and at the same time in the radio you see changes of the jet, and at the same time changes of the disk. You can start to understand how these things are working. Binary black hole, we have OG 287. That's the main object, and it's bright enough to be able to be studied by our technique. And then the most difficult is black hole horizon. I'm not going to speak about that, but of course that's the most interesting, but it's very difficult. Then if you go to 6 meter, the distance between ELT and LSST, for instance. If you do that, then you can reach resolution of typically some tens of picodegree. Go to the full Earth, 10,000 kilometers, then you can resolve the size of the Crab pulsar magnetosphere. You can see what is inside the light cylinder around the pulsar, and see where the peak of the emission, of the optical emission of the Crab pulsar are really emitted. So if you look at a green man on Alpha Centauri, this corresponds to a resolution of femtodegree, and the baseline you would need for that is 5 million kilometers. So currently this is completely excluded, but assuming that this green men and women have also a few meters in size, but I will show you that one can, one would be able to detect slightly larger scales like the construction that maybe these people are doing on their planet, or maybe mountain on the planet. So, as I said, we need to. What we need is an improvement in resolution of 1,000 to 1,000,000, and that's not something that happen every day. So, the techniques that I'm going to explain comes from this paper by Einstein in 25, where he derived the statistics of a gas of bosons with taking into account quantum interaction between the particles. This was the very beginning of quantum physics. And this paper, the Nobel Committee likes a lot this paper. Already 10 Nobel Prizes were given that are directly coming from that paper. The last Nobel Prize was given for the macroscopic quantum tunneling and well, macroscopic quantum effects of a bunch of particles. I am just highlighting here two papers that I am going to discuss again. The first one is the one by Chandrasekhar and Fowler, Physics of Stellar Structure. So this is, of course, the white dwarf, the Chandra mass, and that comes from the degenerate electron, and degenerate electrons come directly from that formula, accepting that this was the one by Einstein, and 1 year Fermi and Dirac independently wrote each one paper that was the same as the one of Einstein, excepting that the plus sign becomes a minus sign, and this was the formula that described the statistics of fermions. Now, if you look at this formula, so this is the if you look at the number of molecules that you have in your bottle of 1 liter, it's about 10 to the 22. So this gives you the variance of the number of particles you have if you are filling zillions of bottles like that. And the first term, this is exactly Poisson statistics, so that's classical shot noise. That's what classical physics tells. And then you have this additional multiplicative term, and this is a quantum correction. And this term here is the ratio between the number of particles in your bottle by the number of quantum phase space elements available. Quantum phase space elements, these are delta X, delta. So the dimension of this number is h at the power of 3 n. 3 is because we are living in a three-dimensional space. So it's a very big number. So usually this number is completely invisible in normal life. Now, if you go to very low temperature, for example, then the number of quantum phase space elements available in the system becomes very low because delta P, you have the energy. And if the temperature goes to 0, basically this term here will dominate the classical part, will become much larger than 1. And that's what happened when you have a Bose-Einstein condensate. So what is Einstein didn't understand really what was happening. He was saying it's like if the particle somewhat interact by a strange wave that he was seeing, that the particle can feel themselves, term that he used in the paper. So what's happening is that when particle wave packets are overlapping in the same phase space element, then the particle become indistinguishable. The two particles, you can then start to describe both of them with a single probability function. And so you understand that indeed, if this density of particle per quantum phase space element that is available in the system become large, then many particles will start to overlap in phase space, and then many of these particles become indistinguishable, and all the electrons would become indistinguishable. Then they are all going to be described by a single probability function, and that's how you can get this macroscopic quantum effect with all the electrons moving in the same way up to macroscopic scales. Now, bosons, photons are also bosons. So I mean, they should follow this type of statistic. Photons are a bit more complicated to describe, let's say. But if photons overlap in phase space, which means their position and momentum vectors are very close together within the uncertainty principle, then something happens. So imagine that you have a source, you have here two telescopes, the atmosphere is there, you have an angle that's the source seen from the two telescopes. So if the angle, the size of the source, the angle is very large, then two photons coming from the source will never arrive in the same with the momentum vector that are very close together, right? Because the angles are too large. So in that case, you have no quantum correlation or very little, and you have only random coincidences between the photons that you detect in the two telescopes. If the angle is small, then or very small, then you could see many photons that become indistinguishable, and when they are indistinguishable, that means that they will be on phase. They will arrive on phase in the two telescope, and that's what we call photon bunching. So this is photon correlation, and then you will suddenly see a lot of photons being correlated in the two detectors. So let's make a step to the 50s. In the 50s, radio astronomy in Europe was done at Jodrell Bank in the UK and in the Netherlands, the other side of the channel, and you see a number of interesting names there. So that was a meeting they had together in 53, and I want to mention a few people. So Robert and Bury Brown, and also Cyril Hazard. He was the PhD of Bury Brown, and they had their name on the papers that were mentioning the first radio source in the sky, radio emission from Andromeda Nebula, from the Cygnus region, from the Milky Way, from the Cassiopeia and Perseus, the supernova, etc. So these people were absolutely fantastic, right? I mean, they changed the way we saw the world. And on the other side of the channel, Martin Schmidt, who is here on top of the antenna coming from remaining from the radar, remaining from the world that they used to do radio astronomy. And now, Bury Brown, we detected the source, but he wanted to understand what was the source, what was the size of the sources. And as I wrote here, if you want to resolve this radio source, you need to measure the structure of the diffraction pattern that we have seen from Augustin Fresnel, and on a distance scale, which is the distance between your telescope, between your antenna, which is wavelength divided by the size of the source, and the baseline that. So the radio telescope were not large enough to do that. So Bury Brown used two different techniques, solved the problem with two different techniques. One moon occultation, so that was the PhD of Cyril Hazard. When the moon was passing in front of a radio source, he could then determine the position of that, the position and the size of the radio source very accurately. And he also invented what he called intensity interferometry. Let me write that sentence he wrote. If the radiation received at two places is coherent, then the intensity of the signal received at those two places is correlated. So this is a sentence which is completely from a person that was looking at light in the way in the form of waves, right? And radio waves, you really like that. You don't see the photon, but you see really the electric field that is doing that pretty slowly on your antenna. Now, this sentence is correct. If coherent, that means the phase of the signal coming of all the photon of the wave coming from your source are coherent. So that's if coherent means in phase, and in that case, indeed, the signal detected by the two antennas should be correlated. Now, the signal is never coherent. Most of those are thermal sources. Even radio sources are non-thermal, but they are not coherent because the phase of the wave at two different sides of the star, of a supernova, whatever, of course, they are not correlated. So his analysis was not correct. This being said, he did it, and he found that there was a correlation between the two radio telescopes. And then he thought, maybe I can try that in the optical. So he did that in his optical lab. He found the correlation with also with optical light, and then he said, okay, let's point to Sirius. He used this projector that were used to illuminate the planes, during Second World War. There are several of them, and so he pointed the two to Sirius, and he was recording more or less the signal and was able to find a delay between the two signals. And when he plots the number of correlation, the signal that was correlated between the two signals divided by simply the amplitude of the signal in each antenna, he found that this is the distance between the two antenna, and he found that the number of this correlation was decreasing with distance, and from that he could determine the size of Sirius as 0.068 arcsecond, which is a very accurate measurement. But again, when you read this paper, it's very funny because I don't know if it's funny, but he didn't understood the physics that was behind. But it was the first time anybody experienced the quantum factor detected photon correlation. It was the first detection of photon correlation ever. Very important step. And you see, when Unbury Brown was showing his results in a conference, Feynman jumped up and said, it cannot work. And the next, and Unbury Brown said, yes, we know, but we were told so, but we built it anyway, and it did work. And the next night, at the middle of the night, Feynman realized the meaning of that observation, and then he woke up on Bury Brown to tell him, yes, you are right, I understand, and he wrote him a letter to apologize for what he said during the conference. So, even Feynman was not able to understand how the things was working. But maybe he was one of the first ones to really understand what was going on. So Unbury Brown then asked for money in the UK system, and the committee, of course, refused his proposal because he said it's not physics, so we don't give you the money. So he went to Australia, which was in the Commonwealth, and then apparently the committee of the Australian committee was much more smart, or had some very clever people, and they gave him the money. So he built this railway with two telescopes like that look like a telescope, and there is a focus, and then with that he could measure 32 stars. Just as a parenthesis, so he was building that with Cyril Hazard, his PhD student. And maybe you remember that, well, Cyril Hazard did his PhD on the occultation of radio sources by the moon. And he realized that in 62, 3273 was occulted 8 times by the moon. And he could observe 3 of them, 3 of the 8 with the Parkes telescope, also in Australia. And you could measure the position of the source, the radio source. 2 sources, 3C and the jet. And of course, he gave this, well, somebody gave this position to Martin Schmidt, and Martin Schmidt discovered the quasars. So these people were really, I must say, they were really genius. Now, there is a revival of, because then the field stopped, because first people didn't really understand what was going on, and then the sensitivity, the electronic, and all of that was such that one can not do much more than observe this 32 bright star. Bright mean sufficiently large also. Now, with Cherenkov telescope, there is a revival of this technique. Here you see a correlation peak that is observed by the MAGIC telescope, for example, and just realize that the maximum of the peak compared to the random coincidences that are here is 410 to the -5. So the peak is very, very, very tiny. And the resolution, timing resolution is nanosecond, so the width of the peak is of the order of 20 nanoseconds.
Signal and the filament signal, including their.
Okay, so I go very fast through a few slides. So the first one that understood what was going on is Ugo Fano. Maybe, I don't know, Remo, if you have ever met Ugo Fano.
Yes,
oh.
Ugo Fano.
Yes.
I am receiving his paper. He was at the University of Chicago and invited me from Princeton to give a talk. Actually, I am on the way. I destroyed the car because it was snowing a lot, and I skipped. But anyway, I arrived in Chicago, and in Chicago there was also his nephew, which you know, because we wrote the first article together with Aldo Treves, who was the nephew of Ugo Fano.
Ah, Aldo is the nephew of Ugo Fano. Ah, I know Aldo. I didn't know that. I know Aldo Treves, but I didn't know he was the nephew of Ugo Fano. Okay.
And we had a great time. And with Aldo was Ugo Fano, who gave us a theorem which we apply, that if you have a rotating magnetic field, it can necessarily imply the presence of a charge as a consequence. He did that from first principle. And this was the result of my paper with Treves, which started the electrodynamics of black holes. Please to send me a review paper. Did not arrive yet. He's trying to find it. A review paper by Ugo Fano, where he made all the theory of this interferometer. It should arrive any day.
Okay, well, you can find it on the internet anyway. 61. Okay, so maybe something else. So Roy Glauber got the Nobel Prize for the development of quantum optics. You can go to the Nobel Lecture website and hear it. It's very interesting. He spent half of his Nobel lecture to explain the Unbury-Brown experiment, and basically to show how important this was. A milestone. It was the start of quantum physics. It was the understanding of this was the start of quantum optics, and then we see all the development that quantum optics get. And the other thing I want to mention is Alain Aspect, who got also the Nobel Prize, but he did something. He did many things, but he did also this Unbury-Brown and twist interferometry using cold atom, and this is used all the time. And here you see, for example, sorry, helium-4, which is a boson. You see the same correlation peak, and this is helium-3, which is a fermion, which is the opposite, because that's a fermion, so that's what you get. And yeah, so okay, so I mean, there are about 10 Nobel Prizes. Well, I've showed some of them, but just on this HBT correlation is really a very, very nice piece of the history of physics, which is not known at all. Nobody teach that at university. Okay, so now what I realized, so I didn't do much, but what I realized is that with current technology, we can make an enormous jump in our possibilities. So we have telescopes which are 1,000 times larger than the one of von Bury-Braun. We can use spectrograph. We can do that at the same time in many spectral channels at the same time. So we can have 10 to the 3 or more spectral channel and study them at the same time. And we also have now detectors which are 10 to the 3 to 10 to the 4 times more accurate. So I am using not nanosecond detector, but picosecond detector. And we gain a lot because we have a systematic reduction, and a term that I don't show in this formula, which is the signal to noise for 2 telescopes. But if you have n telescope, then you add a square root of n telescope in front. Well, in fact, no, you add n telescope because you can do pair. It's the number of baseline that you get, and if you have n telescope, basically you have n square baseline. So just with these 3 things, you gain 10 to the 12 in exposure time, and we have verified that it is working. So it means that you get 10 to the 6 in signal, and 10 to the 6 in signal is 15 magnitude. That's why our technique, with that technique, we can go to sources of magnitude 15 compared to what you obtain in Sirius. And of course, if you have many telescopes, then you can multiply this signal by n, and that allow you to go a bit deeper than that. Now, this is the peak, the correlation peak that you have seen before in MAGIC, with a maximum of the order of a few times 10 to the 5. And look at this red curve. That's what we are getting now. So these are the signals. These are single avalanche photon diode. They are 20 micron in diameter. And they're able to measure the arrival time of photon with an accuracy with a jitter of 5 picoseconds. Then we have electronics. We have a very good clock, an optical clock, and the red curve are real data. It's not a simple. The error bar are smaller than the line width. This is what we are getting. Now, the black line shows the time jitter of the system. The resolution and the sigma is 10 picoseconds. This includes 2 detectors plus the electronics. This is what you get with small angle. If you have large angle, then you get something flat because there are no additional coincidences because of this photon correlation. Now, the plot on the top shows that shows the SNR as a function of the number of coincidences per picosecond that we have here. You see it goes up to 10 to the 7 picosecond coincidence per picosecond, which is a very big number. So, and you see that the curve it goes exactly like the square root. That means we have pure Poisson noise up to 10 to the 7, and this is extremely important. This experiment is all about timing accuracy and systematic reduction. We have been able to get rid of all systematics up to 10 to the 7. This is the highest signal to noise signal to noise bunching peak that exists. I mean that has ever been produced. Now, nice. So now we have to build an instrument. So we want to do that in spectral mode. So each wavelength, we can correlate independently each wavelength channel because two photons will only correlate if they have exactly the same energy. So we are putting the detector, we are building first a spectrometer, that's the first bit. We have built a small spectrometer for 1 meter class telescope. Now we are building spectrometer for 8 meter class telescope. Spectrometers, they are using a grating. And grating are creating a time spread because photons arriving on one side of the grating or the other side, say we'll have an optical path that differs by up to 30 centimeters, something like that. Basically the square root of 2 times the size of the grating. So we had to invent an optical device to compensate for that. And now the jitter that we are getting is of the order of 4 picoseconds for the grating. Then this is the detector. We have to cool the detector to something like minus 30 Celsius. And maybe you see there are six small boards here. Each of them has one of the chip that we are building. So at the end, the total spectrum has a length of about 8 centimeters. This is the chip we have designed. So it took us about 2 years to design it. It's a very complex chip. It has 526 pixel by 16. And we have received the wafer now 1.5 months ago, and we are starting to test the chip. And in principle, the jitter should be of the order of 5 picoseconds for each of the pixel. The efficiency is about 0.2. This includes both the geometrical and the quantum efficiency. So here we can improve a little bit, and we have some development ongoing with a new professor that is arriving at University of Geneva that is developing SNSPD array, so superconducting nanowire, and these detectors allow to have a very wide spectral coverage and an efficiency of the order of 1. These are fantastic detectors, but they need to run at 3.5 Kelvin, so it's a bit more complicated to put that on the telescope. Okay, so this is an image of the spectrum of a source that is there arriving on the previous generation array, which has only one row, and one row is a very big problem because because of the seeing of the atmosphere. Of course, the spectrum has a given width, and if you have a single row, then you lose most of the photon. So that's why we have built this type of detector. Then you can see this is the typical bunching peak that we expect on the sky. This is obtained in the laboratory, and with a maximum of the order of 0.1. And again, if you look at the typical peak that you have in Cherenkov telescope, the maximum is 10 to the minus 5. So that explains, and of course, this is 10,000 times wider than this peak. And that explains why we get so much in signal to noise by going to very low signal to noise. So this is the what we expect as sensitivity per baseline. This is for to noise ratio that of measurement as a function of the magnitude for different couple of telescopes. This is always for. So you see if you have the VLT and the ELT together, that's the orange line that is here that we said before. And of course, if you take smaller telescope like two VLT, this is 2 VLT with the photometer that we have also, and this is 2 VLT with the spectrometer, that's the blue line. And that's where we expect to see 3C273. This is where we expect to see white dwarfs, and that's where we expect to see supernova in 100 megaparsec. And of course, if we have many telescopes, then we can go deeper. So what about the atmosphere? So atmosphere is doing two things. It's doing a jitter. Of course, the photon going through the atmosphere, they go through different refraction indices along the way. And that creates a time spread first, so it could create a jitter, and it also of course create a delay if you have telescopes that are looking at the same source through different thickness of atmosphere or different atmospheric condition. So this is something, you know, this was in my garden. In fact, Raymond knows about it. That's a small celestron, but in fact I am using a small lens which is 2 millimeters in diameter, which is on the top of the telescope. It put the light in the fiber, and the telescope was just there to follow the sun during the day from the morning to evening, and then the fiber was going into our detector, and we were measuring the peak, the bunching peak coming from the sun. The orange line, sorry, the blue data are what we get in the lab, and the orange line is what we get from the sun, and from the difference you can get an upper limit on the jitter of the atmosphere, which is less than 1 picosecond. So jitter is not a problem. Now, the delay is a problem, but when we do what we measure is the intensity of the peak. That's all. We don't measure, we don't use the lag telescope. We only use the intensity of the peak. So the lag is in principle. But there are models that are performing prediction of this, the delay that you have through atmosphere, which have an accuracy of the order of 30 picoseconds. Okay, last point is that we need to synchronize the clock on the two telescopes. So if the telescopes are separated by, let's say, up to 100 kilometers, we can use White Rabbit, which is a protocol developed at CERN to synchronize the two sides of the LHC accelerator. We have tested it over 50 kilometers, so we can install that tomorrow in between ELT and VLT, and we are confident that it will work. Now, if you want to go to Earth scale, that's something a bit different. There are various ways to do that. I don't want to go into detail, but if you want to ask a question, I am ready to answer. Okay, so I want to go to show you a few things that we can do. The first thing we would like to go is go between one VLT and Vista, which is located 1.5 kilometers away. Vista, a 4-meter telescope, and the VLT are 8 meters. Now, this 1.5 kilometers is perfect to study white dwarf. White dwarf, first our prediction of the paper of Einstein 25, basically, that's the degeneracy pressure of the electrons. And we want to test a prediction of the Einstein 25 using intensity interferometry, which is a prediction of the same paper. So this is Sirius B. It's very close to us. It's 2.6 parsec. It's by magnitude 8. This is the mass of the white dwarf, the Chandrasekhar mass. Sirius B is about 1 solar mass, and the radius of Sirius B, if you assume a non-relativistic Fermi gas, is this blue line here. So that gives you the radius in solar radius, a bit more than 1% of the solar radius. But if it is relativistic electrons, and it is the case in Sirius B, that's the radius you expect. And you see that the change is 30%. So just this measurement, with 3 nights on Sirius B, we can get an uncertainty on the radius of 1%. So we can test this type of things on Sirius B, on which... Is it 0 temperature white dwarf? Sorry? Is this 0 temperature radius? So this is relativistic gas, and this is non-relativistic. So I mean, temperature. Sorry? Depends on the temperature. Is the temperature of the electrons? Yes. So okay. Okay. Then here I am showing a Hughes minor room. This is a cataclysmic variable. So we have a white dwarf here, the companion, which is a solar-like star, the accretion disk around it. And you see time to time, maybe on the movie, you will see there, you see a small jet appearing. What's happening is that these disks are pretty cold. The disk is become hotter when accretion takes place. And at the central part of the disk, when the accretion become ionized, because it goes above 3,000-4,000 degrees, then it becomes ionized, and then when the material become ionized, and the viscosity of the disk change completely, of the inner part of the disk. And what happened when that happened, the full inner disk is basically accreted very fast, much faster than before when the material was neutral. And therefore this object shows several peaks per year. Every 3 or 4 months, you have an outburst where the full disk is crashing on the white dwarf, and that's what you see there. It's very regular. We have a light curve like that since 150 years, and almost continues, and it shows that all the time. the duration of each of these peaks is about 3 weeks. That's the time it takes for the full inner disk to crash on the white dwarf. And in 3 nights, we can measure the disk. That's the disk. It's 20 micro arc second in size. We can measure it with an accuracy of angle, the inclination of the disk. We can measure it with an accuracy of 2 degrees. So if we measure during 3 weeks, then we can make an image of the accretion disk that crashes on the white dwarf. Okay, then when we have the VLT and the ELT, sorry, in 2030, and 1 VLT, or even 2, then we can start we get a resolution of 1 micro arc second, and that's enough to look at the accretion disk images. So this is the accretion disk of 3C273. We don't know the mass of the black hole. It's between 10 to the 8 or 10 to the 9. And of course, the accretion disk is much bigger if the black hole is 10 to the 9. So we immediately have a measure of the black hole and also of the inclination of the disk. This is just showing in a Seifert. If you have an alpha disk, this is Shakura-Sunayev, and this is a beta disk. This is Shakura-Sunayev plus X-ray reflection heating of the disk from outside. And the disk, of course, the shape of the disk disk becomes much larger with a beta disk, so we can determine this parameter. That of this Seifert in 1 night is enough if we would have 4 VLT, and with 3C273, which is a bit fainter, we need something like 10 nights of observation. So that's something we can, I mean, you know, we are almost there. Now, the next step, and this I am leading, there is a meeting at ISO to discuss the future beyond the ELT, what are the projects that ISO should select, and we are going to propose that. That means you have the ELT at the center. Now we want to put a series of low-cost telescopes, relatively very bad optic compared to the ELT, but much better than a Cherenkov telescope. So a point spread function of the order of 4. That we can even have some of these telescopes placed on truck, and we can move this antenna in the desert around the ELT up to maybe 50 kilometers along the big road that is across the desert to change the baseline depending on the source that we want to observe. And this is just showing the decrease of the error box that we have between ELT, VLT, and if we have in that case 20 auxiliary telescope, you see we can reduce the error bar of all these parameters. And here we have the inclination of the disk, the phase angle, the inner temperature of the disk, alpha is the slope, the variation of the temperature is radius. So all these parameters are pretty well determined. And in addition to that, as I said before, if we have many baseline, then we increase the signal to noise very much. Okay, I am almost at the end, but one question is, can we do imaging? I have shown you parameter fitting up to now, which is easy because at zero approximation described by few parameters, but you can also do imaging. So this is some simulation that are model independent. So this is in that case, this is the sky image. This is in fact an Einstein ring around the emission of a bright massive galaxy. It's a standard benchmark for all interferometry instruments. And then when you take that image and you put it through the machinery to the simulation of what we are doing, that's what you can reconstruct under different assumptions, let's say. But this is using the clean algorithm, which is very well known in interferometry, but you see that we can more or less reconstruct what we had. Of course, there are some differences. The ratio between the center object and the Einstein ring is not the same, etc., etc. But it shows that we can build real images with this technique. In fact, we have the same information that the Einstein telescope, the Event Horizon telescope had. So I mean, we will have the same problem, and this, but we can do the same, and we will have the same problem than the Einstein, the Event Horizon Telescope had. This is another point where you have a binary system, and you see sometimes you get a third ghost. This is very well known by this technique. Sometimes the algorithm is moving, is taking the brightest star here, and then you make another one here. So I mean, there are some problems like that are known. Okay, so let me finish. So I show again this list of sources. Now. I explained that we can go up to Earth, full Earth observatories. If you do that, that gives you a resolution of 1,000 kilometers at 2 kilo/sec. That's what you need to resolve the Crab pulsar magnetosphere. But that's the same as 1 kilometer at 5 light years, and 5 light years is Proxima Centauri. So that means with that you can get a resolution of 1 kilometer in principle on the closest exoplanet. Now, it's not because you can get the resolution that you can do it. First, this would need to be done in infrared. In the infrared, we are able to separate the light from the planet from the light of the star. In the optical, it's impossible because the ratio is simply too large. But the current instrument like gravity and the VLTI is already able to do that, separate the light from the exoplanet. Now, here we get, of course, a higher resolution than gravity because gravity has 80 meters of baseline, and here we would go to 10,000 kilometers. So we could start to look at maybe the surface of the exoplanet. We don't need 1 kilometer for that, but let's say if we go to 100 kilometers, we can start to see features on the planet itself. Now, if you will put a telescope on the moon and a telescope for the Earth, no, we can record this timestamp anywhere, and then correlate them. There is no problem. We could go to a resolution of 25 meters at 5 light years. So again, that would be extraordinarily difficult to try to start measuring buildings the habitant from this planet would have built, but it's this technique, intensity interferometry, is the only way to get such resolution. There is no other way, simply. So if we can make that work, we still have the problem to have big enough telescope, etc. But as I said to Remo, Michel Mayor is telling me all the time that in 20 years we will have discovered signature of life in the atmosphere of exoplanet. I think that day, even the Pope will start to be nervous, because he has to provide a message also to these people. And I think humanity will want to see what's happening, the day we have good indication of life in the atmosphere, we'll want to know. And I think humanity will be ready to invest. Okay, so summary, these are the main technical improvement, picosecond time, 1,000 square meter telescope, spectral multiplexing, and with that we go from magnitude 0 to magnitude 15, which allow you to do all of these, to look at all these type of sources and more. And as I said, from a resolution point of view, is the only way to go to see detail of kilometer and close by exoplanet. That's it.
Thank you again for this splendid lecture. Let's see if there are questions.
Just Remo asked me to do something on exoplanets, but clearly to be more specific require a lot of simulation, and he asked me that 2 days ago, something. Yeah. So I could not do simulation and things like that.
Yes. Very nice talk. What was the name of the
let's say, as far as we know, there is no physical problem. Now, of course, it has never been done, so we will see. Maybe we discover something in physics, I don't know. But let's say you mean technically, or? Okay, technically.
Physically, like should the photons be coherent?
No. First, this works only for non-coherent. If you do the experiment that I have shown you, we have done it with a laser. Laser is that every photon has the same phase. You don't see any peak. The phase needs to be random, so it has to be incoherent. If you have this was shown also by Hugo. When you look at this paper, it's very clear. It only works because the phase part of the probability function. If you put the phase, if they all have the same phase, the term including the phase can go out of the sum of the probability function, and then when you average it over time, then you get zero, so you get no correlation. You need random phases. I mean, there is a lot of technical difficulties if you want to go to Earth scale that are needed, but in principle, and I didn't mention that, but the synchronization is a big problem. But the Chinese, they have put a very accurate clock on their space station, and they have been able to synchronize different ground stations to picosecond level. So we know that it is working. And okay, maybe you have to use the space station to synchronize your telescope, but it has been done, so we know it technically it is working. Now with the moon, synchronizing the moon and the Earth to picosecond, that's another. I didn't thought about that.
Very good. Okay. The questions. Certainly, test Moses' theory, looking at separation between the little red clouds and the closest galaxy.
So we make the calculation this afternoon. The little red dots are very big. They are galaxies. They are too big. Well, they are faint, but they are too big. We are looking to very small angles.
Okay. Also about the baseline. So if the baseline is very long, will the signal be like exhausted during the transportation?
No, because at each telescope we store the arrival time of each photon on the detector on that telescope. And then you send the timestamp by plane or by internet or whatever, and at some point you go somewhere, you correlate them, so there is absolutely no problem. It's very, and that's the problem of Michelson interferometry, because to do fringes between two telescopes is very difficult. And so with VLTIs, I've been able to do it up to 100 meters, let's say. But to do that in kilometer, if you want to do that between Vista and VLT, I think this is being discussed. You need to make a tunnel, which is 1.5 kilometers, in which you need to have complete vacuum, and the photon needs to go from the two telescopes through that tunnel, and you make the fringes somewhere. So it's really very challenging. And then the atmosphere is a problem. The atmosphere is a big problem. So because of the atmosphere, with Michelson interferometry, you can only do that in the near infrared, but not in the optical. But okay, mid-infrared is also good. And yeah, so it's much more delicate. This is straightforward. I mean, when you have the technology, it's relatively easy. Neutrons are very thin in the optical. Usually we use Hubble telescope to really detect anything. So eventually we get really quick at so if you look at the pulsar, I mean, you can only do that with a bright object, but magnitude 15 is okay. the crab pulsar, you look only at the peak, you remove everything else. And you have to do phase result measurement. So you only keep the photons that are in the peak, and you do the image only with these photons. And then one should be able to see from where they are coming from. Okay, one believe that the optical peak of the crab is made inside the light cylinder, and probably relatively close to the boundary. But yeah, this is exactly the type of thing we can start to probe if it's outer gap.